In eastern Washington state, there's a waterfall that, at first glance, doesn't look like the beginning of some great mystery. It isn't stunningly tall. It doesn't throw so much water over its edge that you immediately think, yes, that's the power of nature. Put it next to the most famous waterfalls on Earth, and honestly, it fades almost immediately. No dramatic height, no monstrous flow, none of that postcard power you usually expect from a natural record holder. But that's exactly the strange part. This modest waterfall was probably carved by the largest flow of water ever to move across the surface of the Earth. At least the largest one whose traces people have been able to recognize. And to me, this is one of those cases where a landscape's appearance is more misleading than a great trailer for a bad movie. If the word flood gives you the usual image in your head, that image is almost certainly too small. Make it bigger, then make it bigger again. And even then, the scale probably still isn't enough. We're talking about an event so large that the modern Earth can't come anywhere close to producing it today. The flow that cut this waterfall and reshaped the surrounding landscape has no equal among the processes happening on the planet now. That's why the place is so disorienting. If it was really that enormous, the landscape feels like it should look like the aftermath of a disaster, torn open, terrifying, obvious. But today, the country around it is dry. You can drive through it for an hour, then another, and almost nothing changes. Where the ground is level, there are wheat fields. Where it looks stripped bare, dark basalt shows through, ribbed, raw, unfriendly. Sagebrush, wind, a lonely farm here and there, a huge empty sky. The kind of place where your first thought is, nothing ever happened here. Nothing screams water of unimaginable force. It feels sunburned, exposed, harsh, and deceptively empty. But that dryness is exactly what hides the story of water so powerful that ordinary comparisons start to sound too small. And if someone told you that almost everything around you had been remade in a matter of days, you probably wouldn't believe it. And you'd be wrong. Here's what we know for sure. Traces of a massive flood are scattered across the entire region. There are cliffs sliced open. There are deep, dry channels where nothing flows today that comes anywhere close to matching their size. There are strange landforms, as if someone dragged a rough tool across the earth and didn't bother smoothing the edges. There are boulders sitting in places where no ordinary river could have carried them under any normal conditions. You can argue about one clue forever. A rock might have cracked. A channel might have dried out. A boulder might be explained by some one-off quirk of nature. But when all of it sits together, when one trace starts explaining another, the picture becomes much harder to ignore. What emerges is a story so unbelievable that even specialists resisted it for a long time. And honestly, that's the most human part of the whole story. The problem wasn't just the rocks. The problem was that the conclusion sounded too bold, too catastrophic, too unlike the careful version of geology where landscapes change slowly, patiently, almost invisibly. To me, that resistance makes sense, but it doesn't make it any less remarkable. Sometimes the evidence is right under your feet, and accepting it is harder than finding it. It took geologists decades to admit that these catastrophic floods really happened. One man was mocked and pushed aside for more than 40 years because of this idea. He received his medal only after a huge delay, when the Earth itself had basically already made the case. I'll come back to that story later, because it contains a rare moment. Science doesn't just change its mind. Sometimes it has to be forced. But let's not get ahead of ourselves. Once the recognition finally came, the story became bigger than a dispute over strange terrain in Washington state. It forced geology to rethink how the face of the Earth forms in the first place. It can change slowly, by fractions of an inch, over thousands of years. And sometimes it can change in a few days when a force arrives that breaks every familiar scale. Local farmers had already given this land a name. In places where the fertile topsoil looked scraped away and bedrock showed through in patches like old wounds among normal fields, they called it scablands, land that looked like a scab. It's a rough name, but an accurate one. There's nothing pretty about it, but it captures the feeling of a surface that wasn't merely exposed, it was truly scarred. Later, one American geologist sharpened the name. He called them the Channeled Scablands, and that was much more precise because the rock here isn't just bare, it's cut through, carved up, crisscrossed by a network of dry channels, as if not a knife but an entire river had turned into a blade and scraped across the land. That's the mystery. An ordinary-looking waterfall that doesn't belong on the cover of a travel magazine, and the traces of an event that may have been the largest flow of water on Earth's surface. The calmer the landscape looks today, the stranger it becomes to imagine that water once moved through here with enough power to rewrite the map in a very short time. To read these scars correctly, you have to understand the main question: where could that much water have come from? Not just a lot of water, not a severe flood, not a big river spilling over its banks, a flow so huge that it left marks across an enormous region and made scientists argue for decades. So where did all that water come from? To understand that, we have to go back to the very end of the last ice age, somewhere between 12,000 and 15,000 years ago. On a map, the region looks familiar enough: Western Canada, Washington, Idaho, Montana. But back then, so much ice covered the land that normal geography basically stopped working. Almost all of what is now Western Canada was buried under a huge ice sheet. Geologists call it the Cordilleran ice sheet, but it's easier to picture one continuous field of ice stretching almost unbroken from Alaska down toward the modern border between Canada and the United States. And this wasn't a neat white cap sitting on mountain peaks. Frozen fingers pushed south from the ice sheet, long tongues of ice that reached into the valleys of Washington, Idaho, and Montana, slowly remaking everything they touched. And for that, we have to go back to the end of the Ice Age, to a wall of ice, and to an inland sea that stood behind it, until the whole system reached its weakest point. So right now, we're looking at only the first mark on the ground. What if behind it wasn't a local disaster, but one of the greatest floods our world has ever seen? To make this less abstract, an ice sheet isn't mountains under snow. It's a continuous mass of ice, in places 3/4 of a mile to about a mile thick, sitting across a huge part of the continent. Snow doesn't melt there, it piles up. Under its own weight, the whole mass begins to flow downhill, outward into any valley with room for it. A finger is one of those tongues of ice squeezed into a mountain valley. It moved through that valley like a very cold, very patient bulldozer. Not quickly, but behind it nothing stayed the same. One of those tongues of ice ended up in a deep mountain valley in western Montana, in the Clark Fork River Valley, near the place where the river heads towards Lake Ponderail. And it didn't just creep up to the river, it crossed over it and blocked its path. That sounds almost ordinary. Ice blocked a river. But don't picture an iceberg drifting quietly somewhere on the horizon. This was a wall, an ice barrier that rose about 2,000 feet and at its widest point stretched roughly 30 miles across, all wedged between mountains like a cork in a bottle. And when a cork like that sits in the path of a river, the water can't politely go around it. It has nowhere to go. The river keeps bringing in runoff, rain falls, glaciers melt. Year after year, all of it builds up behind the ice wall. The water level rises, lowlands disappear, and an ordinary mountain landscape slowly turns into something else entirely. Because behind that dam, what formed wasn't a pond. It wasn't even just a big lake. It was an inland sea. Geologists call it Glacial Lake Missoula, a name that feels almost absurdly modest for what it was at its peak. Water stretched hundreds of miles up the valleys of western Montana. It was more than 2,000 feet deep. The lake stood so high that entire mountain ranges became islands, while passes and slopes became lake bottom. And here's the number that makes everything click. About 500 cubic miles of water. That's more than Lakes Erie and Ontario combined. And all of it was held back not by a stone gorge, not by a concrete dam, not by engineers. It was held back by a wall of ice. And ice, as we'll see, has its own mind. Try to picture it. You're standing somewhere on a summit in western Montana. Below you, there are no valleys and rivers. There is water to the horizon, calm, cold, the color of cloudy glass, with occasional white patches of icebergs breaking off from the distant wall. Neighboring mountains are islands. What is now a road pass was then underwater. And all of it is held back not by rock or concrete, but by ice that has plugged the only exit like a cork in a bottle. This sea really existed. That's not a guess or a pretty reconstruction. You can still see its traces today. Climb the slopes above Missoula, Montana, on Mount Sentinel or Mount Jumbo, and you'll notice faint horizontal lines, as if someone drew long, pale marks across the hillside. Those are ancient shorelines.
The marks formed where the water stayed at one level long enough to cut into the slope. Then the level changed. The water rose higher, paused again, and another line appeared. They look like stains on the sides of a giant bathtub. Exactly how many times the lake filled and dropped is hard to say, but the slopes remember.
And now we've reached the dangerous part. Every ice dam has one fatal weakness. Ice is lighter than water. In a real sense, it floats. Water pushes against it, undercuts it from below, searches out every crack, and slowly tries to lift the whole wall, even when from the outside it looks motionless and permanent. So the main question is no longer where did the water come from? The question is, what happens when 500 cubic miles of water press against a wall of ice? Would that dam stand for centuries, or was it a time bomb that simply hadn't clicked into its final step yet? So what happens when 500 cubic miles of water press against a wall of ice? Sooner or later, that wall gives out. As I said, ice is lighter than water, and water eats away at it. When that much water gathers behind an ice dam, it does everything at once. It pushes against the wall, it melts it, it tries to lift it. At first, the dam holds. 1 year, 2 years, 10 years, it stands. But the water keeps looking for a way through. And at some point, it finds one, a narrow crack somewhere under the dam along the very bottom. Under that kind of pressure, it has to find it. It's only a matter of time. And then the clock starts. Water moves under the ice. It widens the crack. It melts the ice with its own heat. A trickle becomes a tunnel. The tunnel becomes a collapse, and the wall that looked eternal starts to lose. Here's where we should slow down, because this isn't the ice quietly melted over the summer. This is a chain reaction. The more water rushes through the tunnel under the dam, the more friction it creates. The warmer the water gets, the faster it eats the ice around it. The tunnel doesn't expand over months, it expands over hours. The ice above it loses its support, it sags, it cracks, and above all of that, the 500 cubic mile lake is still pressing down. At some point, the barrier stops holding across its full height. It doesn't melt away, it breaks. From the bottom up, and what had been a wall turns in a matter of hours into a hole and a mass of floating icebergs. And when a wall like that fails, it doesn't look like the ice slowly melted. Imagine it for a second. A 2,000-foot barrier of ice suddenly stops being a barrier. It tears open. It floats upward. It breaks apart into icebergs. And through the breach comes not a stream, not a river, but an entire lake. Most of what had been building behind the dam for years pours out, and not over weeks. Estimates suggest that the main draining took about 2 to 3 days. 2 or 3 days, and a body of water larger than some American states rushes out through Idaho and Washington. In the time it takes to read a long book, an inland sea simply disappears. How much water are we talking about? The flow that burst out of the valley was roughly 10 times greater than all the rivers on Earth combined. Not like a severe flood, 10 times the entire river flow of the planet,
all at once from one mountain valley. By some calculations, the roar of the collapsing dam may have rolled across the entire Northwest, a sound on the scale of an entire region. This kind of event, the sudden outburst of a lake held back by ice, has its own word. It comes from Iceland, where similar events still happen today, though on a much smaller scale. Jökulhlaup. It sounds like a spell, but it simply means a glacial lake outburst flood. Iceland had one in 1996, dangerous, impressive, and big enough to make the news everywhere. But next to what came out of Lake Missoula, it would have looked like a thin stream from a faucet.
A couple of numbers help catch the scale. In the narrows of the Clark Fork, all that water had to squeeze through a passage only about half a mile wide. Picture a bottleneck draining a lake. Geologists estimate the peak discharge there at about 9.5 cubic miles of water per hour. Farther downstream, it doesn't get much easier to comprehend. About 500 million cubic feet of water per second racing through canyons. For comparison, that's 60 times the Amazon. Not some small river, the Amazon. And now comes the twist that turns a single catastrophe into a machine that ran again and again. The dam came back. The thing is, a glacier isn't rock, even if that's how we tend to imagine it. Under its own weight, especially when there are hundreds of feet of ice, it slowly flows, heavily, reluctantly, like very cold tar that can't be rushed. After the flood punched an opening through the dam, maybe about a mile wide and roughly 2,000 feet deep, ice from both sides of the valley began creeping back into that gap. Not in one day, but after weeks, maybe months, the Clark Fork was blocked again. The lake started filling again. Rain, meltwater, river runoff, all of it built up behind the wall again. And then the wall failed again, and again, and again. Picture that rhythm. For several decades, an ordinary mountain valley, a river, forest, quiet. Then the dam gives way, and for 2 or 3 days, the largest flow on Earth tears through that valley. Then the ice slowly creeps back, the lake fills, and a generation later, it happens again, and again, and again. Around 89 times, maybe closer to 100, over roughly 2,000 to 2,500 years. And for almost all of that time, no one was counting. There was only the land, taking hit after hit.
The earliest lakes were the biggest ones, the full 500 cubic miles. But year by year, the ice sheet thinned. Each time it held the valley at a slightly lower level. Each new Lake Missoula was a little smaller than the last, and each new flood was a little less monstrous. Though less monstrous here still means a wall of water taller than a skyscraper, moving at the speed of an express train. So the question now isn't, did this happen? It isn't even how enormous was it. The question is, where did all that water go? 500 cubic miles, almost 100 times. It didn't just evaporate in that Montana valley. It went somewhere. And if you follow its trail, you find something strange. It left its mark even 1,000 miles away on the floor of the Pacific Ocean. So, let's follow the water.
From the Clark Fork, the flood roared into northern Idaho and immediately gouged out a basin for itself. That's the basin where Lake Pend Oreille sits today, one of the deepest lakes in North America. In a real sense, it's a flooded fjord, ripped open by ice and floodwater working together. Then the water charged into eastern Washington. But the path ahead wasn't empty, and this part matters right away. Not all of the water came from Lake Missoula. The northern edge of the Columbia Plateau ran straight up against the foot of the ice sheet, and another tongue of ice was pushing down onto the plateau from there, the Okanogan Lobe. You can still see how far it got. Along its southern edge lies a long ridge of stones and debris, the trash the glacier pushed ahead of it and dropped when it finally stopped. And beyond that ridge, the land is scattered with thousands of foreign rocks, from small boulders to blocks the size of houses. Granite and similar rock sitting in a country of basalt where it has no business being.
They were carried in by icebergs the size of oil tankers, broken loose and sent drifting by that glacier. And the ice tongue itself was its own machine of destruction. As it melted and fell apart, water ran across its back and burst out from underneath it. Where those jets converged, they formed channels and began chewing into the ground. That's how Moses Coulee formed, a 40-mile wound in the landscape, the second largest canyon in all the Channeled Scablands. Today, a thin little stream runs along its floor. It doesn't come close to explaining that trench. And nearby, right in the middle of a wheat field beside the road, stands Jaeger Rock, a stone block torn whole from a basalt cliff about 15 miles to the north. Subglacial water ripped it loose and carried it here. 400 tons, 20 feet tall. It stands there as if something absurdly large dropped it and never bothered to come back. Meanwhile, the water from Lake Missoula had its own problem. While the lake itself was trapped behind an ice dam in Montana, that same Okanogan Lobe had already crossed the Columbia River and blocked it too. Behind this second plug, another lake had formed, Glacial Lake Columbia, roughly where Grand Coulee Dam stands today. And when the Missoula flood reached that point, the valley that was supposed to receive it was already about 1/3 full. All that water simply couldn't fit, so it backed up. It filled every available space. Then it went over the top. It spilled across land, over low passes, out of the Columbian Basin, and into the next basin to the south. And here's the main point of this whole chapter.
The flood didn't politely follow the channel of one river the way normal water does. It climbed over divides, it jumped into neighboring valleys, it spread across the open plateau in several arms at once. And wherever the old canyons couldn't handle it anymore, it cut new channels for itself. That's how it flooded the Quincy Basin and stood there hundreds of feet deep. The resort town of Soap Lake would have been buried under more than 600 feet of water. Then the water spilled out of the basin through a whole fan of new channels along its edges. And where it spread out and slowed down, it dropped a layer of sediment about 130 feet thick and scattered foreign rocks across 600 square miles. Where the water hit steep terrain again, it cut one cascade after another, and each one worked differently. In some places, it formed a waterfall. At Potholes Coulee, a waterfall about 1.5 miles wide plunged more than 800 feet and exposed columnar basalt. Those stone columns we'll come back to later because they aren't random here. In other places, the flood didn't make one clean channel at all. In the Drumheller channels, it carved a chaotic maze, more than 100 separate channels, some cut 300 feet down into the rock across 12 miles of ground. And the Palouse River had its fate rewritten completely. It captured it, bent it almost at a right angle, left its old valley to dry out, which is now the dry Washtukna Coulee, and sent the Palouse through a new canyon toward a new waterfall, Palouse Falls, nearly 200 feet high, a dramatic horseshoe cut into bare basalt. In 2014, students from the town of Washtukna persuaded lawmakers to make it the official waterfall of Washington state. So the state, in a way, chose as its symbol not some timeless natural beauty, but the trace of a catastrophe that passed through in a matter of days.
Then all of it converged at one point. Wallula Gap, a narrow cut about 2 miles wide in the Columbia River Canyon, and through it, by some estimates, a volume of water equal to the entire river flow of the planet was trying to squeeze through at once. Obviously, the gap was too narrow. The water couldn't drain fast enough, so it effectively dammed itself. Behind Wallula Gap, the water level climbed and a temporary lake formed there, Lake Lewis, about 3,000 square miles, twice the size of Rhode Island. The backwater even pushed upstream along the Snake River for more than 100 miles, all the way back into Idaho. It stood there maybe a couple of weeks, maybe a little longer. Then it vanished again, as if it had never existed. West of Wallula Gap, the flood entered the Columbia River Gorge. This is an 80-mile slot through the Cascade Range, in places 4,000 feet deep, and the only sea-level corridor through that mountain chain. The gorge already existed. The floods didn't cut it from scratch, but they tore through it hard enough to leave marks everywhere. The water moved as a layer about 1,000 feet deep and accelerated to roughly 70 miles an hour. It widened the gorge, it deepened it, it sliced away the old, gentler slopes and left near vertical walls. Oregon's tallest waterfall, Multnomah Falls, drops today from one of those sliced-off walls, more than 600 feet down. And Crown Point, a huge rock promontory, more than 700 feet above the river and 300 miles from where the flood began, would still have been underwater with room to spare. Behind one of the narrows in the gorge, yet another short-lived lake briefly formed, Lake Condon. When the gorge opened out near present-day Portland, the flood spread and slowed, but it didn't stop. The water stood so high that if the city had already existed, only the tops of the tallest buildings would have stuck out above it. The east side of modern Portland and the long ridge above nearby Vancouver now sit on thick layers of sand and gravel dumped by these floods. That ridge is basically a giant gravel bar, and later half a city was built on it. North of there, the water backed up again and pushed into the Willamette Valley. It flooded the valley under as much as 400 feet of water all the way to Eugene, more than 120 miles to the south. That created another temporary lake, Lake Allison. It settled out as thick silt, and when the water drained away, that silt became some of the most fertile farmland in the country. The last 60 miles carried the water down the Columbia toward the ocean, to Astoria. But even there, the story didn't end. When the river met the Pacific, the floodwater didn't behave like ordinary river water. It was colder than seawater and far denser because it was carrying a monstrous load of rock, sand, and mud. So it didn't spread across the surface the way a normal river would. It dove. It slipped beneath the ocean water and kept running along the sea floor as a turbid current, an avalanche of water and suspended sediment. If you need an analogy, it's like the underwater cousin of a burning volcanic ash flow, except made of cold mud. That flow rushed into the submarine canyon or Fastoria, fanned out across the ocean floor, ran through an undersea channel and across a flat, deep plain for hundreds of miles to the south, and finally settled in a deep basin called Escanaba Trough. There, it left a layer of sediment about 400 feet thick at a depth of roughly 10,000 feet, more than 600 miles from the place where it left land. A flood that began behind an ice wall in a Montana valley ended on the floor of the Pacific Ocean.
So it left its calling card almost everywhere, in Idaho, in Washington, in Oregon, and on the ocean floor. But here's the catch. All of this happened 15,000 years ago, and the water is long gone. So how do you see it? What does a flood like that leave behind on land? Something you can point to and say this is what the flood did. So how do you see a flood nobody saw? The fingerprints of that giant water are scattered across the Northwest. The problem is that they're so big, the ordinary eye refuses to believe them at first. So let me show you how to read this land. Start with the most obvious thing, the Channeled Scablands themselves. If you look down at central Washington from above, you see a landscape carved by old, interwoven channels. The channels bend around uneven ground exactly the way a normal creek would. At first, nothing seems strange. Then it hits you. This dry stream bed covers a huge part of the state. That's the Channeled Scablands, a place where the flood stripped away the soil, broke into the bedrock beneath it, and left behind a tangled network of bare stone passageways. The first farmers who tried to plow it saw only ruined land. In reality, they were standing in a riverbed, not the size of a valley, but the size of an entire region. Next come the coulees. These are deep, dry canyons, clearly cut by water of tremendous force. Today, if anything runs along their floors, it's often just a thin little stream, and it can't explain their size at all. The biggest is Grand Coulee. With its upper and lower sections together, it stretches about 60 miles. In places, it's 1,300 feet deep and 3 miles wide. Remember how the Okanagan lobe blocked the Columbia? That plug forced enormous volumes of floodwater to move south along its edge. That diverted flow carved Grand Coulee.
An 800-foot waterfall worked inside it, and it didn't stay in one place. It migrated upstream, gnawing away at the head of the canyon. Across repeated floods, it retreated for dozens of miles. The entire upper Grand Coulee above today's dry falls is basically the path that waterfall took backward. On the way, it wrapped around Steamboat Rock and left it standing alone, a mile long and the same 800 feet high.
On top of that rock, there's still a glacial boulder dropped by an iceberg after everything around it had already been scooped out and carried away. The second major canyon, Moses Coulee, we've already seen, the one water cut directly from beneath the melting ice. And roughly in the middle of Grand Coulee is Dry Falls. This is where a person's sense of scale breaks down fast. Today, it's a huge horseshoe of bare cliffs about 400 feet high, twice the height of Niagara, and by some estimates about 5 times wider, more than 3 miles from rim to rim. But during the strongest floods, this wasn't a waterfall in the normal sense. The edge of the cliff was buried under another 200 to 300 feet of muddy, debris-loaded water. What looks today like a 400-foot wall was then just a shallow dip on the surface of the flow. The water didn't fall over Dry Falls. It moved over it and around it, ripping out rock as if it were quarrying stone. If that doesn't fit in your head, it isn't supposed to. To this water, a 400-foot cliff was a small, uneven spot on the floor. The third sign is stone blades. Across the region, narrow ridges and buttes stick up from the ground. Somehow they survived the impact, long ribs of basalt that the flood either didn't have time to tear out or couldn't quite tear out while it was scraping everything else away.
Umatilla Rock stands right on the floor of Dry Falls. The Twin Sisters near Wallula Gap, 2 towers about 300 feet above the present river, would have been under 800 or 900 feet of moving water during the flood. If that water had held on another day or 2, it probably would have torn them away too. And on the eastern edge stands Steptoe Butte, a 1,000-foot hill that rose like an island above the edge of the flooded country. The fourth sign, stones that floated in. Across this basalt country lie boulders of granite and gneiss, from small ones to house-sized blocks, scattered hundreds of miles from the nearest place where that kind of rock naturally occurs. They didn't roll here over land, they floated. The flood carried whole fleets of icebergs broken from the ice sheet. Inside those blocks of ice were stones frozen into place. An iceberg runs aground, melts, and the cargo is left wherever it stopped. One such giant lies high on a slope near Wenatchee, Washington. Its mass is estimated at about 18,000 tons. Others traveled even farther across the Cascade Range into western Oregon. Canadian and Montana granite ended up in places where by any ordinary logic it should not exist. One of these travelers even has a name and an address. On a hill in the Willamette Valley stands Erratic Rock, a 40-ton block of argillite, about 600 million years old, the only rock of its type outside Canada. It was carried on an iceberg more than 500 miles down the Columbia system. Today, a paved path leads to it past a vineyard. You can stand beside a piece of another continent delivered here by water. But among all these floated-in stones, one seems designed to test whether we're really willing to accept the scale.
In the Willamette Valley, people found the largest meteorite in North America, an iron mass of about 15 to 16 tons, roughly 10 feet tall. There was no impact crater nearby, and for a long time that looked strange. A mass like that from the sky, but no sign of where it hit. The explanation sounded even stranger. The meteorite probably fell somewhere in Canada or Montana, became frozen into glacial ice, and then one of the Missoula Floods loaded it onto an iceberg and carried it several hundred miles down the Columbia. The iceberg melted in the Willamette Valley, and the iron block simply settled where the water dropped it, about 13,000 years ago. After that, ordinary boulders stop feeling like the main evidence. They become part of a vast fleet carried by this water. And the fifth sign is the quietest looking one, but also the hardest to argue with: ripples. Anyone who's been to a beach has seen small sandy ridges left behind when a wave pulls back, inches high, inches apart. Now imagine that same shape enlarged hundreds of times on the floor of a valley in Montana or on a gravel bar along the Columbia, in places where there's no water at all today. At West Bar on the Columbia, a mass of sand and gravel stretches for about 5 miles and in places sits 250 feet above the present river. Its entire surface is covered with current marks 20 to 40 feet high, with an average spacing of about 360 feet between crests. A similar field of giant ripples was found on Camas Prairie in western Montana. Elongated hills spaced hundreds of feet apart, rising dozens of feet, fanning out from a mountain pass. And that field holds the record. Individual crests rise about 50 feet, as high as a 5-story building, with something like a football field between neighboring crests. They're considered the largest known current ripples on Earth.
The ripples you've seen on a beach are inches tall. Here, they're stories tall. These are ripples on a riverbed. They are made by water moving across the land fast, wide, and deep. And to me, this is what settles it. You can argue with the channels if you want. You can try to explain away the coulees, but it's almost impossible to read these ripples honestly as anything else. There's one more marker, less spectacular, but beautiful in its own way. The flood left behind fertile soil, just not where it started. The rich, dark soil that drew settlers west, the soil of the Willamette Valley that made the Oregon Trail worth so many lives, is in large part ground stripped by upstream floods from the Scablands and carried west. The pioneers weren't just plowing good land, they were plowing flood deposits. Put it bluntly, the first farmer in this region was the water itself. So the ripples settle the case. This was a flood, huge, fast, deep. But one question remains, the one we've been carefully circling the whole time. A river takes millions of years to cut a canyon. This flood lasted only 3 days. So how did a flood that lasted only for about 3 days manage to carve canyons hundreds of feet deep into solid rock? Something doesn't add up, unless the answer lies in the rock itself. This is the question we've been circling the whole time, and it's an uncomfortable one. We're used to thinking of erosion as slow. A river cuts into rock year after year, millennium after millennium, sometimes for millions of years, slowly deepening its channel. That's how the Grand Canyon formed. But here, we have a flood that lasted only a few days, and it carved canyons hundreds of feet deep into solid rock. How is that even possible? The answer doesn't start with the water.
It starts with the rock itself.
And here's where the story makes a strange little loop. The inland northwest sits on basalt, but that basalt formed long before the Ice Age during a completely different kind of flood. Millions of years ago, huge cracks opened in the ground here. What came out wasn't an explosive storm of ash, the way we picture a typical volcano. It was enormous volumes of fluid lava. It spread across the lowlands layer after layer until it built up an entire plateau, the Columbia Plateau. Geologists call this layered stack of rock the Columbia River Basalt Group. It covers more than 60,000 square miles, and in places it's more than 2 miles thick. So the land that would later be swept by a flood of water had once been buried by a flood of lava. One flood prepared the stage for another. And flood of lava isn't just a metaphor. These were among the largest lava outpourings Earth has ever seen. Fissures opened for dozens of miles, and molten rock poured out, not in explosions, but slowly, like an overflowing river. It covered the lowlands layer after layer, sometimes 100 feet at a time, over and over for thousands of years, until an entire plateau had built up. That was the surface that the water would later attack. And basalt gave the flood exactly what it needed. When basalt cools, it cracks, and often it doesn't crack randomly. It breaks into tall, regular columns. Many of them are almost perfect hexagons, like someone built a honeycomb out of stone, except each cell is the size of a cliff. The rock is strong and heavy, but it's already divided into pieces. So when the Missoula Floods tore into this country, they weren't facing one smooth, solid wall of stone. They were facing rock that had already been pre-cut into pieces. And with rock like that, the flood didn't have to be delicate.
It didn't need to grind the cliff down grain by grain the way an ordinary river does. It only had to grab a ready-made column, wrench it out of the wall, and carry it away. And water moving 80 miles an hour, carrying icebergs, uprooted trees, and a boiling slurry of boulders along the bottom can absolutely do that. It doesn't slowly polish the rock. It rips it out in chunks, almost like someone taking apart an old stone wall. That's how you get a canyon in 3 days instead of 3 million years. So now we have the how, a lava plateau, columns like a stone honeycomb, rock already split into blocks, water moving 80 miles an hour. Today, that's a normal textbook explanation. But science took a painfully long time to get there, and the man who first put these pieces together, the man who first read this story in the land itself, was mocked by his own profession for about 40 years, and not because of the rocks. So what was it? This is where, to me, the most human part of the whole story begins. Let's start with the awkward part. No one was standing next to this flood with a notebook. Nobody wrote down what happened. Nobody took measurements. Nobody filmed it. So where does the confidence come from? How do we know it happened this way? One extremely stubborn man spent almost his entire career answering that question. And he wasn't arguing with some outsider or amateur. He was arguing with his own profession. His name was J Harlen Bretz, and here's a small detail, but it says something about him. The J in his name wasn't an initial, it was his entire first name, Bretz insisted there shouldn't even be a period after it. The man who would spend his life arguing with the way things were supposed to be was unusual even in the way his name was written.
He was an American geologist, and because of this one story, he would spend more than 40 years at odds with almost the entire field. And do you know where it began? Not with an expedition, not with an excavation, with a map. Sometime shortly before World War I, Bretz was studying a topographic map of the Quincy Basin in central Washington, and one detail stopped him cold. Its shape looked exactly like a gigantic Niagara Falls, a double cascade, an island in the middle, a gorge extending downstream. The geometry of a major waterfall was all there, except it sat on the edge of a basin where there was no water, and where, as he understood, no river had ever flowed. So Bretz asked the simplest possible question: what is this doing here? About 10 years passed before he finally got out into the field in the early 1920s, and what he saw on the ground only made his suspicions stronger. The landforms looked like a dried-up river channel, but many times larger than anything a normal river could leave behind, and in some places there was no water nearby at all. Bretz was good at reading the surface of the earth, and the surface was telling him one thing: a flood had passed through here. In his first paper in early 1923, he still didn't fully understand how monstrous that water had to be. That same summer, he returned to the field. And sometime during that season, as he later described it, the light came on. You can picture how that happens. You spend day after day walking through the landscape. You look at dry channels, cleanly sheared rock, boulders sitting where they don't belong. Then, at some point, the details stop being separate oddities. They lock into one picture. And the picture is almost too big to say out loud.
The area is too large. It's all connected. To explain the traces here, there, and farther away, you need water at least 200 feet deep, rushing through the whole system at once. Not a large flood, not a bad spring runoff. Water on an unimaginable scale. By his second paper that year, the field evidence had left him no choice. He called the event the Spokane Flood, and he gave the scarred landscape the name we still use today, the Channeled Scablands. Remember that one American geologist who refined the name at the beginning? That was Bretz. His colleagues did not respond with enthusiasm, and that's putting it mildly. Bretz had pushed against a powerful current inside geology. He challenged an idea that science had only recently fought hard to establish and was not eager to give up. That idea was called uniformitarianism. The basic point was simple. The landscapes we see today were shaped by the same slow, steady processes we can observe right now. Rivers cut banks, weather breaks rock apart, glaciers grind surfaces down, and all of it happens over enormous spans of time. The Grand Canyon, carved by its river over millions of years, was the perfect example of that view. Uniformitarianism had replaced an older way of thinking, catastrophism,
the idea that Earth's forms could be made by sudden, violent events. The problem was that catastrophism reminded many scientists a little too much of the biblical flood. At one point, that distrust became more than background noise. It almost became a trial. In January 1927, the Geological Society of Washington invited the young Bretz to present his work. But in practice, they lined up 6 senior geologists against him. Bretz later called them his challenging elders. Each one had a calm explanation for the Scablands that did not require any giant flood.
The goal seemed pretty clear: publicly dismantle Bretz's argument and close the subject. Bretz called it an ambush. One contemporary described it almost like a lynching. After that meeting, he sank into depression for several months. Then he did a very Bretz-like thing. He wrote to every critic, asked each of them to lay out their arguments in detail, and answered them in a published paper. And here's the strange part. Joseph Pardee was sitting in that room. He already had evidence that supported Bretz, but Pardee worked for the US Geological Survey, and he stayed silent. So the argument slowly became more than scientific. It became human, and sometimes silence weighed as much as words. Geology had only just earned its reputation as a rigorous, respectable science. Then Bretz came along and said Central Washington required a wall of water unlike anything the modern world had ever seen. To many influential people in major universities and inside the US Geological Survey, that sounded like a step backward, almost like a return to superstition. So now the argument wasn't only about rocks, it was about pride, reputations, and institutional authority. When a scientific idea becomes dominant, people sometimes defend it even after it's time to calmly examine the uncomfortable question. One of Bretz's fiercest critics was Richard Foster Flint of Yale. Flint insisted that the channels of the Scablands had been carved by ordinary streams and rivers that were somehow overloaded with their own sediment. Audiences nodded along with Flint, even though Flint himself never went out to see the evidence with his own eyes. But Bretz did have a real weak point, not in what he saw on the ground. The weak point was the source of the water.
He could show the scars on the landscape. He could walk you through them and explain why they looked like the work of a gigantic flow. But where did all that water suddenly come from? Something almost like an inland ocean. And why was it released so quickly? He couldn't give a clear answer. And as long as that question remained open, the skeptics weren't going anywhere. Some of them were very powerful figures. Worse, Bretz himself doesn't seem to have fully understood how important that gap was to everyone else. He was a field man. The landscape spoke clearly enough to him, and that was enough. So when the answer was sitting almost right in front of him, he didn't pick it up. And to me, this is the most frustrating part of the whole story. Because the answer already existed. Someone had already found the lake. He had even written Bretz a letter, and Bretz never answered. The answer really did already exist. In fact, it existed long before Bretz ever walked through the Scablands. In Montana, a very careful geologist with the US Geological Survey was studying the region. His name was Joseph Pardee.
Back in 1910, Pardee published a paper showing that an enormous lake had once stood in this part of the country, held back by an ice dam. This was Glacial Lake Missoula, the same lake whose ancient shorelines can still be seen as horizontal bands on the hills above the city of Missoula. Bretz almost certainly knew about this publication. In fact, in his early papers on the Scablands, he even cited Pardee's work. The water source for his own theory was basically sitting on his bookshelf for 15 years, and he walked right past it. Then, in 1925, Pardee sent Bretz a letter. It came just 6 weeks after one of Bretz's papers, the very paper where Bretz ran straight into the central question: where had such a mass of water come from?
Pardee's message was simple: my lake may be the source you need. And Bretz didn't develop the idea. Why? At this point, we can only guess. Maybe it bothered him that the idea wasn't his. Maybe he wasn't convinced. Maybe it was just stubbornness. Pardee didn't push the connection into the public debate either. He was a government geologist. He had supervisors above him at the Geological Survey, and they were not exactly sympathetic to Bretz. Then the Great Depression began, which was not the ideal time to become an extra headache for your bosses. So the source of the water almost became orphaned. The second half of the proof was lying right next to the first, but nobody seemed eager to put the two together. Later, around 1939, Pardee returned to the western edge of his old lake. He went back to something he'd only noticed in passing before, and this time he looked closely. On Camas Prairie in Montana, he found an entire field of huge, long hills. Each one was 2 to 3 miles long. They stretched away from a mountain pass, and the pass itself looked as if water had once blasted through it with incredible force. These were ripples, but not ordinary ones, giant ripples. The distance from crest to crest was hundreds of feet. Some of the individual waves in the landscape rose dozens of feet high. Remember those giant current ripples on Camas Prairie I mentioned earlier in passing? Pardee was the one who finally read them. A calm lake just sitting in place doesn't leave marks like that. Those marks form when a lake suddenly and rapidly drains. Pardee wrote a paper about it. The title was almost comically restrained for such a discovery: Unusual Currents in Glacial Missoula. The year was 1940. That June, the Geological Society of America met in Seattle. On June 18th, in the afternoon, there was a session devoted to the Channeled Scablands.
Richard Foster Flint was in the room too. He spoke first, laying out a careful, polished version of the gradualist argument. The channels, he said, had been carved by ordinary water flows. No catastrophe, no sudden, monstrous flood. At that moment, the room was more or less on his side. Then Joseph Pardee stood up. According to accounts, he was not much of a speaker. He was nervous. He sounded uncertain. He didn't even name Bretz directly. But he did what mattered. Without drama, almost matter-of-factly, he put on the table what Flint did not have: the giant ripples of Camas Prairie, what they meant, and the conclusion that followed. The water had drained suddenly, and there had been an unimaginable amount of it. The room felt it. The rustling of papers stopped. People stopped glancing around. The same room that had been nodding along with Flint a few minutes earlier was now really listening.
because the argument Bretz had been unable to support for more than a decade had just been supported for him. When Pardee finished, silence hung for a few seconds. Then the room rose and applauded. In the old argument, where Bretz and his impossible flood had stood alone against cautious defenders of slow processes, the decisive missing piece had just appeared. And still, acceptance did not come right away. More years passed. World War II got in the way. So did a very ordinary problem. Some of the best evidence lay in remote places that were hard to reach. Only in the 1950s did Bretz himself, by then nearly 70, return to the Scablands. He spent one last summer there with colleagues. In 1956, they published a major paper, almost 100 pages long. They went back through nearly every important feature, answered the competing explanations, and printed photographs of giant current dunes right on the surfaces of gravel bars.
These were the kind of photographs that make an argument hard to keep defending. You look at them once, and the old explanation starts to fall apart. Once the field evidence was laid out in that kind of detail, and Pardee's lake finally supplied the needed source of water, the debate was, as one geologist later put it, more or less crushed by facts. A few stubborn opponents remained, but overall geology accepted it. The Spokane flood had really happened, and its scale had been enormous. Then, in 1979, more than half a century after Bretz first began talking about colossal water, and more than 40 years after the harshest ridicule, J Harlen Bretz received the Penrose Medal. It was the highest honor his science could give him. And there was something almost cruel about that late recognition. Bretz was 96 by then, the oldest recipient in the award's history. According to the story, when he learned about the medal, he said something to his son along these lines: "All my enemies are dead, so I have no one to gloat over." It's funny, but the man laughing had waited far too long for the obvious to become acceptable. There's another story about James Gilliuli, one of Bretz's old and hardest critics, a man who had once called his ideas simply absurd. Late in life, Gilliuli finally went to the Scablands. They say he stood for a long time in silence before one of the great dry cataracts. Then he laughed and said something like, "How could anyone have been so wrong?" For decades, he resisted the flood idea. Then the landscape, seen with his own eyes, changed his mind in a single day. Bretz carried that burden of rejection for almost 40 years, from the late 1920s into the 1960s.
Today, geologists often tell this story as a lesson about science, that ideas should be defended when the facts support them, and that it's dangerous to cling to an old explanation just because it's familiar. But there's a second lesson here too, and people who know the history well tend to speak about it more carefully. It is very rare for one person to solve a major mystery entirely on their own. Bretz got the headline, but Pardee found the lake and the giant ripples. Other researchers added pieces too, their names now sitting quietly in old publications, mostly forgotten. Science is made by many hands, and it's not always easy to say whose piece mattered most. So the rebel finally got his medal. The establishment eventually gave in. This story almost seems to have a happy ending, except it still wasn't over.
because the version of Bretz's victory that ultimately survived was not the version Bretz himself had spent his life defending. Here's what makes this story such a good cure for overconfidence. Even after Bretz won, the version of his victory didn't hold up on the ground. For most of his career, Bretz argued that there had been one flood, one event, exceptional, unrepeatable, almost impossible in scale. Even for people who had accepted the flood itself, that was hard to swallow, again because of the scale. If there had been only one event, then the 17-mile coulee leading down to Dry Falls had to be carved in roughly 3 days. That's hard to believe, even with all the evidence.
But by the late 1970s, a new generation of geologists had started reading the rocks differently. And what emerged wasn't a gentle correction. It was almost a new catastrophe laid on top of the old one. The unsettling part wasn't just that Bretz had the number wrong. It was that one blow had turned out to be a whole series of blows. In Burlingame Canyon, one exposed section shows about 40 of these layers. For weight, each bed meant a separate flood. Not one great episode, but dozens, maybe as many as 100 events, as the waters of glacial Lake Missoula raced to the sea again and again, century after century. At first, this idea also stirred up arguments, much like Bretz's own theory had once done. Resistance, competing explanations, researchers arguing with one another. But if you look closely at the field evidence, there's not much room left for another reading. And the ancient shorelines on the hills above Missoula, those lines on the walls of the giant bathtub, were saying the same thing. The lake filled, it emptied, it filled again, it drained again, over and over.
Then the rock started revealing details that felt almost like detective work. In the Walla Walla Valley, these layered deposits, known as the Touché beds after the town of Touché, lie like a stack of pages. Each page, coarser at the bottom and finer toward the top, is one flood. It hit hard, then faded. And between some of those pages, there's a bookmark, a thin layer of volcanic ash from Mount St. Helens, about 16,000 years old. That bookmark does two things at once. It helps date the floods, and it proves they were separate events. The ash settled quietly on top of one layer, then the next flood laid down another layer above it. In some places, researchers even find two of these bookmarks between two flood beds, with ages decades apart. That means at least that much time passed between those two blows. And there was more. In those layers, researchers found buried rodent burrows and animal bones. That means that after a flood, the land had time to go back to ordinary life. Something dug burrows again. Something walked across that soil. The world acted as if it was over. Then the water came back. By those counts, there were about 75 floods before the S set ash, and more than 30 after it. So the familiar phrase, around 100, may not be an exaggeration at all. It may be cautious.
Then traces of the floods turned up offshore. At the mouth of the Columbia, in submarine canyons, geologists found the same muddy bottom flows that carried sediment out into the ocean. Farther out still, in Escanaba Trough, on the deep sea floor, they identified 12 separate flood layers, with thin layers of ocean clay between them that could be dated. In other words, 12 events are recorded there. But there's an important catch. Most likely, only the largest floods created flows powerful enough to leap across the deep sea channel and travel that far south. If that's true, 12 isn't the full count, it's the floor. The smaller floods simply never made it into that record. We can see the big ones. Exactly how many smaller ones there were, no one knows. And one more thing is worth keeping in mind. The Missoula Floods weren't even the only megaflood in this part of the world. Around the same time, farther south, another huge lake overflowed, Lake Bonneville, the ancestor of today's Great Salt Lake in Utah. It broke through a natural barrier in Idaho and sent more than 1,000 cubic miles of water down the Snake River at close to 70 miles an hour. That flood carved a canyon in the Snake about 600 feet deep, created Shoshone Falls, and filled the river channel with melon gravel, rounded basalt boulders, some of them the size of a person. In effect, it made its own Channeled Scablands across the Snake Plain. So the same corner of the Northwest was being reshaped at the end of the Ice Age by two different catastrophes at once. And the Snake Valley, which also took the backwater surge from the Missoula Floods, got hit twice. Even now, both professional and amateur geologists return to these places every year. They look again at the outcrops, the bars, the ripples, the dry channels, and they read the landscape all over again. The story changes not because the rock has changed. The landforms Bretz described are still carved into the ground, but the science around them is alive. New tools appear, new observations appear, new ways of fitting the data together appear. The story of the glacial floods is still being written. And this turn mattered far beyond one patch of Washington. Once geologists had to admit that a sudden violent event really could reshape the face of a whole continent, the way they thought began to shift. It became clear that the slow, steady processes uniformitarianism was built on weren't enough to explain the entire history of Earth. Catastrophism, which had long been treated almost like an embarrassing word, got a seat at the table again. After that, fast catastrophes began to look useful for other stubborn mysteries too. The moon, scientists now think, may have been knocked loose by a collision between the young Earth and another young planet. An asteroid killed the dinosaurs. So the Missoula Floods didn't just remake the Northwest, they helped geologists think more broadly about how worlds are made at all, ours and others. Science moves, the rock stays where it is, and Bretz, with all those scars in the ground, is still right. But if you decide this story ended 15,000 years ago, that would be a serious mistake. The flood still hasn't let go of the Northwest. People there live inside it every day. Almost no one notices. It's very easy to file all of this under ancient history, close the subject and move on. But the floods never really left the life of the Northwest. The people there live every day inside a landscape made by that water, and most of the time they don't even know it. Take drinking water. Beneath the Rathdrum Prairie and the Spokane Valley lies one of the region's major aquifers, and it exists because floodwaters burst out of a narrow passage, spread wide, and left behind enormous thicknesses of gravel. Today, that gravel holds water for about 400,000 people, and it's so loose and coarse that water moves through it unusually fast, in places close to 60 feet per day. It's one of the fastest large aquifers in the United States. The government has even designated it the sole source of drinking water for the whole area, In plain terms, there is no backup. So the people there, if you want to put it poetically, are literally drinking the speed of the flood. The lakes of northern Idaho, Coeur d'Alene, Hayden, Pend Oreille, and others sit in basins the floods either scoured out or dammed, and Pend Oreille is so deep it almost sounds impossible by itself, 1,100 to 1,200 feet of water, with another 1,000 to 1,500 feet of sediment beneath it. That puts the rock floor of the basin hundreds of feet below sea level. That's why the US Navy keeps a submarine testing range there, roughly 500 miles from the nearest ocean. The lake is deep, quiet, far from heavy shipping and curious eyes, a natural, silent proving ground with nothing else like it nearby. Locals jokingly call it Area 51 for submarines. A flood-scoured hole in Idaho is used to test some of the quietest submarines in the country.
Grand Coulee Dam, the largest concrete dam in North America, doesn't stand where it stands by accident. Nature had already done the main engineering work. The channel was already cut by the flood. People only had to block it with a dam, raise Banks Lake, and send water to about 650,000 acres of farmland across the Columbia Basin. Roads and rail lines across the inland Northwest often follow corridors once carved by floodwater, and even the concrete of the region, the concrete in its bridges, buildings, and roads, is often mixed with that same flood gravel, mined from bars and alluvial fans left by the water. Geologists put it simply, the towns there are literally built from the wreckage of an earlier world. The Scablands have played stranger roles too. In places, this terrain looks so much like parts of Mars, with the same scoured channels and the same feeling of a flow that came, passed through, and vanished, that engineers tested a rover prototype in central Washington before sending similar machines to another planet. Planetary scientists also used the Missoula Floods as a working model for what might have happened on Mars, and maybe beyond Mars too. Over time, the federal government tied this four-state landscape together as the Ice Age Floods National Geologic Trail, an attempt to turn one enormous event into a coherent story. It doesn't fit inside one park, one monument, or even one state.
And Mars isn't just a pretty analogy for the ending. The largest flood channels in the solar system aren't on Earth, they're there. Kasai Valleys stretches for more than 1,200 miles, and in places its width reaches hundreds of miles. That's many times larger than any Earth channel of this kind. When Mariner 9 sent back the first detailed images of Mars in 1971, and geologists saw those enormous riverless channels, they immediately thought of Bretz's Channeled Scablands. Since then, the Scablands have become Earth's main field guide for reading Mars. The geologist Victor Baker even wrote a book about it, The Channels of Mars. It's a strange thing. To understand another planet, people first had to believe in an impossible flood at home. And there's another side to this story, the quietest one. The floods happened very recently, 13,000, 14,000, 15,000 years ago. In geology, that's practically yesterday afternoon. By then, people were already living here. In the creation stories of the Nez Perce and the Palouse, there are flood motifs that echo strangely with what is written in the ground. It's very possible that human eyes saw that inland sea, and it's very possible that somewhere downwind, human ears heard the ice wall finally give way.
If so, it may have been the loudest sound any person ever heard on this continent. Not thunder, not an eruption, a low roar that made the ground shake and went on for hours. Someone stood on high ground and heard an entire sea leaving, and then, maybe, they told the story. And the story kept moving for thousands of years until it reached us as myth.
Some traces of this story still have not just a scientific name, but a human one. That giant meteorite was called Tomanowos by the Clackamas people, ancestors of the Confederated Tribes of Grand Ronde. The name means guardian spirit. Today, it stands in the American Museum of Natural History in New York. But in 2000, the museum and the tribe reached an agreement. The Grand Ronde keep the right to hold a private annual ceremony at the stone. So the ancient flood suddenly becomes more than a layer in the ground. It becomes part of a living memory that continues inside a museum hall. And that waterfall in eastern Washington, the one that doesn't seem especially remarkable, is still there. It looks like an ordinary detail in an ordinary world, a world that seems to have been built slowly and patiently. But that impression is misleading. Almost everything around it was cut not over endless ages, but in a matter of days by water that rose hundreds of feet above the ground, where a person could stand today. This place is like a story written in stone. Most people walk across it without knowing how to read a single line. But once you learn the alphabet, bare scabbed rock, dry cataract, traveled boulder, ripple the size of a hill, you can't look at this country the old way again. And you can't quite look the same way at the slow, patient earth we think we know so well either. So, what do you think? How many places around us seem eternal when really we just haven't learned how to read their history yet? The earth likes leaving notes. Very few people know how to read them.